All right, so we're in this chapter, we're analyzing systems and components, really looking just at components that plug into larger systems. Things like nozzles and diffusers and pumps and turbines, compressors, heat exchangers, throttling devices. And so often we have an open system analysis for each of these components. There's some mass flow in, some mass flow out. Some of them have heat transfer in, some of them have shaft work out. So you have M dots like that. And it's just the same equations applied to a large variety of applications, a large number of applications. We talked about the nozzle last time, did we not? What's the purpose of the nozzle? To really increase the exit velocity. That's the purpose. Is it to transfer heat with the surroundings? No. Is it to produce shaft work? No. It's to really come out with a high exit speed. How does it work? You have to push it through the restriction. And so the inlet pressure is greater than the exit pressure. And we solved the problem last time. The opposite of a nozzle you may not have as much experience with. It's called a diffuser. But we have a lot of diffusers in application, maybe not as many in engineering applications as nozzles. We have a lot of nozzles in a lot of places. But there are some diffusers. What does a diffuser do? Usually it's increasing the area. I'm exaggerating the increase in the area. What would it do to the speed of the fluid as it goes into a larger area? What would the velocity do? It would slow it down. It's going to slow it down. Here's the hard one. If the pressure in a nozzle, the inlet pressure and the exit pressure is less than the inlet pressure for a nozzle, what do you think the pressure does for a diffuser? Just the opposite. Just the opposite. So the outlet pressure goes up a little bit compared to the inlet pressure. That throws students for a loop. It's slight pressure recovery. There's a slight pressure recovery in a diffuser. So liquid water enters a well-insulated diffuser at a given pressure, 300 kilopascal, 4 degrees C, and 10 meters per second, through a flow area given to be 0.03 meters squared. So there's a lot of information in that first sentence. Maybe we want to go ahead and make some illustration. Diffuser, show it as gradually increasing area. Okay. Inlet 1, outlet 2. We'll have a control volume around it. And so there's only one inlet, one outlet for this device. Okay. Let's list some of the information given. Pressure 1, 300 kilopascal. Temperature 1, 4 degrees C. And I'm just going to underline it, liquid water. When you see liquid water at 4 degrees C, what goes off in your brain? What are you saying to yourself? It's liquid. It's not two-phase or superheated. It's in a very dense state, right? High density. And what about the special temperature of 4 degrees C? What about the density of liquid water as you go from 5 to 4 to 3 degrees C? Something special happens at 4 degrees C. It's the most dense it's going to get. So if you're at temperature above 4 degrees C, 10 degrees C, and you start to go colder, 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 it's getting denser, 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 ever so slightly, a very small amount. It hits 4 degrees C. Now you continue to cool it. Guess what water does? Expands, expands, ever so slightly, but it does expand. And on freezing, it really expands. All right, so that's a special feature of water. Okay, so at 4 degrees C is its densest. Can you tell me what the density of liquid water is at 4 degrees C? It's like the nominal value. If I say, give me the density of water at 20 degrees C, they'll often just round it off and they'll give me the density of water at 4 degrees C. What is it? What's the density of liquid water? 1 gram per cc, how many kilograms per cubic meter? 1,000. So 1,000 kilograms per meter cubed. Okay, if that's it, what's the specific volume? .001 meter cubed per kilogram. Again, I'll repeat that statement. Normally, if I said, I need to do a back-of-the-envelope calculation quickly, I have liquid water. What's the density of liquid water? I don't care if it's 20 degrees C, 25 degrees C, 10 degrees C. I'll throw out 1,000 kilograms per cubic meter, and I'll run with it. Okay? All right. So this is telling you that it's liquid water, and we have rho 1 is 1,000 kilograms per meter cubed. All right. And the area 1 was given to be 0.03 meters squared. It exits with a velocity of 8. So I forgot to put the velocity. It's 10 meters per second. And so the velocity exit is 8 meters per second. Does that look reasonable? Did it speed up or slow down? It slowed down. That's what a diffuser does, doesn't it? Yeah, that looks reasonable. Water behaves as an incompressible substance. What does that tell me about the density at 2? It's the same. What about the specific volume at 2 compared to the specific volume at 1? The same. It's incompressible. The inlet temperature is the same as the outlet temperature. What about the temperature at 2? Same. So it didn't change temperature. It didn't change density. It's liquid water going through a pipe that gradually increases in cross-sectional area. We call it a diffuser. The internal energy is only a function of temperature. So if I said, I don't know what U1 is, but you know what? I know what U2 is. It's the same as U1. Internal energy didn't change. True? True. Assuming steady state operation, calculate these 3 things: the mass flow rate through the diffuser. I'm trying to say nozzle, but through the diffuser. What's the mass flow rate? So would we say that the mass flow rate is the volumetric flow rate coming in divided by the specific volume coming in, or the mass density coming in times the volumetric flow rate coming in? All right, so the mass flow rate would be 1,000 kilograms per cubic meter times the area coming in times the velocity coming in. Professor, make our exam questions that easy. Please, please, please. All right, so we get m dot of 300 kilograms per second. Done. Part B. What is the exit area? How would I calculate the exit area? Give me the overarching principle that I'm going to employ to start my approach to calculate the exit area. Conservation of mass. Conservation of mass. True? So we know that the conservation of mass says mass flow rate in is equal to mass flow rate out. Mass flow rate in, density in, cross-sectional area in, velocity in, density out, cross-sectional area out, velocity out. True? The densities cancel. So the exit area is equal to the inlet area times the ratio of the inlet to exit velocity. All right, so we're going to have 0.03 meters squared divided by 10 divided by 8 meters. The units cancel, and we get left that A2 is equal to 0.0375 meters squared. Notice that if I left it as a ratio, area 2 over area 1 is, I think, 1.25. This is a 25% increase in the area flowing through the system. Last part, exit pressure. How are we going to do it? What principle are we going to use? Overarching. Conservation of mass? We already used it. Conservation of energy. Applied to the open system identified by the control volume as shown. You can write the whole equation down. I don't have a lot of room, do I? So I really think I should write the whole equation down. Let me erase a little bit here. And I think I'll try and tuck it in right down in here. The rate of change of energy for that control volume as a function of time is equal to the rate at which heat is being transferred in, that would increase it, minus the rate at which you have shaft work going out of that system, plus we're going to have a mass flow rate coming in at 1, bringing with it its enthalpy at 1, bringing with it its kinetic energy at 1, bringing with it its potential energy at 1, taking out at state 2, its enthalpy at 2, its kinetic energy at 2, and its specific potential energy at 2. Which of these terms are 0, and why is that term 0? Steady state. Why is this term 0? It's a well-insulated diffuser. Most diffusers, even if you weren't given that information about being well-insulated, you would typically assume it because otherwise, what is Q dot? I would need to be able to estimate it some way. So sometimes it's explicitly stated in the problem statement. This one, it's well insulated. Q dots is 0. But let's jump over to why the change of potential energy is negligible. Because not the problem told you to neglect it, but there's no information to calculate it. There's nothing about the elevation in and out. And it's not a very big device. So every indication is assume the change in potential energy is negligible. All right. How about the shaft work? It's 0 because it's a diffuser. There's no shafts in or out of the diffuser. It's not explicitly stated in the problem statement. But you got to know something about diffusers. All right. Now, at this point, we could say that the mass flow rates are the same, so they're going to cancel each other. It's not that they're 0, but they cancel on both sides of the equation. And we're left with the bottom line equation that the inlet enthalpy plus the inlet kinetic energy equal to the exit enthalpy plus the exit kinetic energy. That all make sense? Where did we get that equation? Professor, I need to find that equation quickly on my equation sheet during the exam. No, reestablish that equation quickly during the exam from the overall principle of conservation of energy. I need to scroll down. Let me scroll down a little bit. Hate to do that. Now, I'm going to do this. U1 plus P1V1 plus 1/2 V1 squared is equal to U2 plus P2V2 plus 1/2 V2 squared. These V's right here on the V squared, that's the velocity or the speed. Why can we cancel U1 and U2? Same temperature. The water didn't heat up or cool down. It's incompressible. It's a function of temperature. It's same temperature, same internal energy, done. So what we find is that the final pressure, the exit pressure, is equal to the inlet pressure plus 1/2 V1 squared minus V2 squared divided by the specific volume, because V sub 1 is equal to V sub 2. It's just V, the specific volume. It's incompressible. True? Ready to plug numbers? So we plug a number and we say, okay, it comes in at 300 kilopascal. We have 1/2. We have the velocity coming in is 10 squared minus the velocity going out, 8 squared, meters squared per second squared. Let me put the units a little different. Meters squared per second squared. And then we have the specific volume or multiplied by the density, either one. Here, put it 0.001 meters cubed per kilogram. True. And then I think, I got to get the units to work. So what is a Newton? A kilogram meter per second squared. What's a Pascal? A Pascal is a Newton per meter squared. And the last, but don't forget it, do not forget it, do not forget it. What is that little k in front of the Pascal? Kilo. So one way of handling the kilo is just say, what's a kilo? It's 1,000. Isn't it? I mean, that's almost too trivial, but don't make an error with the kilo. So when you jump onto the calculator, and all these units will cancel correctly as shown, we find that the exit pressure, 318 kPa. Did it go up? A diffuser is a pressure recovery device. The good diffuser, the pressure will go up in the diffuser. Somebody says, I am so lost, I don't believe it. All right, let me try to appeal to something that we're going to get to later, but it's near the end of chapter 6 when we get entropy considerations brought into play. Isentropic process. We'll basically rederive equation that you already know. It's called Bernoulli's equation. Who's heard of Bernoulli's equation for fluid flow along a streamline, steady state? So guess what? Here's your streamline from 1 to 2. You're going to say, why don't we just use Bernoulli's equation, Professor? Because we're in thermodynamics and we're solving, using different strategies, but you're going to get the same equation. What was Bernoulli's equation? Maybe I'll tuck it in right here. Bernoulli. I can't spell his name. No, I think that's close enough. Bernoulli, right? What is his equation along a streamline from point 1 to point 2? What is that equation, Bernoulli's equation? The pressure plus 1/2 rho v squared plus rho gz is equal to a constant anywhere along that streamline. Who's seen that one? You heard of Bernoulli. A lot of hands went up. But is this Bernoulli that you remember?
They have it equal to the same thing on the other side.
Well, that's what I meant by a constant. So you say along that streamline, state 1. First of all, is there changes in z elevation? So I'm going to knock that out. P1 plus 1/2 rho V1 squared is equal to P2 plus 1/2 rho V2 squared. Isn't that a correct application from state 1 to state 2 flow through this device? Just do a little algebra. P exit is equal to the P inlet plus 1/2 rho times V inlet minus V exit squared. Hey, look at this equation right here. What do you think? We went in circles. No, we didn't. We just had the same result derived using a different strategy. All right? But to really do a good job of Bernoulli, we really have to have entropy concepts. And entropy concepts, though we have no irreversibilities, frictional effects are negligible. That's one of the requirements in Bernoulli's equation. It's inviscid fluid, inviscid flow. So there you go. Hopefully all that appeals to you and makes sense. Let's talk about a pump, but I think we did a pump problem last time, didn't we? So what is the black box called a pump? What's the purpose of a pump from 1 to 2? You want the exit pressure to be a lot higher than inlet pressure. That's the purpose of the pump. A pump is usually applied to liquids. If it's a liquid, the pump really doesn't compress the liquid and making it occupy a smaller volume. So the specific volume 2 is approximately the same as specific volume 1. The purpose of the pump, not to compress it, that's a compressor. It's to boost the pressure. Pumps operate on liquids. Vapors and gases, that's a compressor. All right. We solved the problem about a pump last time. I think this is the problem we solved, didn't we? So we need to keep going through our list. The next is a device called a turbine. There's a hydraulic turbine, there's a gas turbine, there's a steam turbine, so there's a bunch of different turbines, but they all take an inlet fluid stream, state 1, outlet fluid stream, state 2, and they have a shaft that comes out of that turbine, and it's providing mechanical power to something else. If this is a steam turbine in an electric generating power plant, that it drives an electric generator to make electricity to sell it to customers. Okay? So this is a turbine. If it's a hydraulic turbine, same thing, but it's usually liquid water in and out. And you have a dam, a hydroelectric dam. They have hydraulic turbines. All right. So it's a power-producing device. Typically, they are well insulated. If you go to a power plant, say, hey, I'd like to see a turbine, they'll show you a big, puffy, little white type of cloudy thing. Well, it's basically wrapped in insulation, like a zippered on layer of insulation. When they want to service it, they take the layer of insulation off, put it to the side, and work on it. But when it's operating, it's under a blanket. It's under this insulating blanket that's installed on it for a steam turbine. All right, so its purpose is not to transfer heat with the surroundings. It's to produce a lot of shaft power coming out. How does that happen? Well, you apply the first law for this control volume around the system. Typically neglect changes in potential energy, elevation. And what you'd find is that this is equal to the mass flow rate, one inlet, one outlet, times high inlet enthalpy, low exit enthalpy. It comes primarily at the expense or the difference in the enthalpy. And if you had a change in the kinetic energy, a lot of times that's small, so it's neglected. But if you included it, it could come in fast and go out slow. And so it would be a change in the kinetic energy there. But that's the energy balance for that open system around a turbine. There's a lot of great videos on the internet, isn't there? If you want to see something, you want to learn something. How many people go there if they have a problem with their automobile and they want to fix it? Yeah, I go there too. It's like, hey, I have this squeaky sound. Where is it coming from in this model and year? There's all kinds of things for repairing your home. Well, learning engineering, and actually how many people learned calculus from a person straight up the road on the internet? Patrick? JMT? He's probably making a whole lot more money than me. He's good. He's good. I met so many students, that's how they learned calculus. They say, yeah, I listened to the instructor. All I tried to figure out from the lecture was what are they talking about. Then I'd go back, get that key word, and listen to Patrick explain it to me. It's true. Well, let me do this. Let me see if I can play this. And it's worth listening to because I think they do a pretty good job because it is a dynamic system.
In today's video, we will understand stators, rotors which are moving attached to the hub.
That's good enough. Stators, and rotors. But I think that's a pretty good quick definition or trying to describe. Notice we studied nozzles. Inside of steam turbines, there's nozzles to redirect and to accelerate the flow for the right orientation and speed for the next blades of in the rotor section. So that's pretty good, I think. Actually, a pretty good description of what's going on. Let's jump back to here. This problem I solved already for the 9 o'clock. So what I'm going to do is I'll post that, throw it up there on the internet. But I'm going to solve a compressor problem. There's a lot of different compressors. You can have reciprocating compressors or centrifugal compressors, just like a centrifugal turbine, like we just looked at. So just like a centrifugal turbine has rotors and stators, you also could have the same thing for a centrifugal compressor. But let's just put it, here's a black box. It's called a compressor. I have fluid flow coming in at state 1. I have fluid flow going out, state 2, typically one inlet, one outlet. But the compressor doesn't have a positive W dot coming out. This, if you want to stay with the sign convention, is negative. What does that mean? I have a negative power out. You've got to feed shaft work to the compressor to make it work. That's why we would stay with say that is a negative W dot CV. Compressors often are not good heat exchangers. They may not insulate a compressor to prevent any heat transfer from it, but often we just assume it's negligible. Again, that's a difference opinion. Okay, think about it. I have a steam turbine. I'm trying to get all of that energy out of the flowing steam and convert as much to useful shaft work. If I have any going to the room or surroundings, that's going to be a loss. I want to avoid it. If you have a compressor, let's say an air conditioning compressor in your house, you look at that compressor, it's not insulated. Guess what? If you have a stray heat transfer from the shell of your compressor in your, at your house, it's okay. It's only going to help a little bit. But they don't, it's hard enough to build a good compressor. It's really difficult to build a compressor and heat exchanger all in one device. What they do is they connect the fluid that comes out of the compressor to a heat exchanger, and then the combination is what you want. But often this is a standard assumption that they're well insulated or they're adiabatic, hence there's no heat transfer with the surroundings. You apply conservation of mass, conservation of energy. Let's solve a problem. Refrigerant 134A enters a compressor at 2.4 bar, 0 degrees C, and exits at 12 bar and 60 degrees C, and the mass flow rate's given. So maybe I just draw it like this, and I'll say here's inlet state 1, here's outlet state 2, and I'm going to stay with the positive W dot CV out of the control volume, knowing that it's going to be a negative power. And I just try to organize all my information. There's refrigerant 134A. It has a mass flow rate of 1.7 kilograms per second. It's going to be operating steady state, so m.1 is equal to m.2. I'm going to not worry about the subscript. In is equal to the out. And then we have the pressure at 2.4 bar. And let me try and scoot this over a little bit. Maybe I put it over here, state 2. What about the pressure at 2? It's 12 bar. I look at that. Does that make sense? The pressure went up? Yeah, it's a compressor. The purpose of the compressor is to boost the pressure. The temperature inlet, 0 degrees C. The temperature outlet, 60 degrees C. When you're smashing that refrigerant together, things get hot. Anybody ever used a tire pump as a kid, and you just worked and worked and worked, and you're up and down, pushing on that tire pump? And then you ever felt the outlet to the tire pump, how hot it was down there? You should. Sometimes if you really pumped a lot, you'll burn your finger. Why is it so hot? Where's the flame? What's being burned? Nothing. All that mechanical energy you're putting into it is increasing the pressure, but it's also increasing the temperature of that air, and you can feel it on the outlet. Go find a tire pump and do it, okay? It's interesting the first time you experience it. It's like, wow, how did that get so hot? Same thing here. You're compressing refrigerant. It's getting hot and high pressure. Now, we also have, heat transfer to the surroundings occurs. Notice, they tell me that Q dot is to the surroundings at a rate of 0.4 kilowatts. So it's negative 0.4 kilowatts in my traditional sign convention of Q dot's positive in. All right. Determine the power input to the compressor. So this is what you're asked to find, that power input. Now, because they said input, maybe it's like a free body diagram in statics. You turn the direction of that vector around. Maybe I turn the direction of Q dot and W dot around, but I switch the sign then in my energy balance equation. I take responsibility for that plus or minus sign in my energy balance equation. Let me just say I'm going to determine the power output from the compressor, and I'm going to calculate a negative answer. All right. Now, so that's what I'm looking to calculate. So we do our control volume, And we write our energy balance equation. Rate of change of energy and control volume with respect to time is equal to Q dot in minus W dot CV out. If I'd have changed the direction, I'd have put a plus there. But I didn't. And so that's why it remains a negative sign. Plus the mass flow rate in times its enthalpy in. But you know I'm going to have the same mass flow rate out, and I'm going to subtract the enthalpy out. Just like I have plus the kinetic energy in, I'll have the minus kinetic energy out, and the potential energy in minus the potential energy out. So I shortcut a little bit because I didn't want to write two m dots. And so you see, there it is. Steady state. What about changes in kinetic energy? Is there any information given to me in the problem statement to help me calculate the change in kinetic energy? No, and it's negligible, assumed to be negligible. What about the change in potential energy? Same logic, nothing given about elevations. You'd assume it's negligible. So what we find is I'm looking to calculate W dot CV. It's equal to Q dot plus M dot H1 minus H2. True? So I go to the tables and I say, is there any way I can get enthalpy at state 1 for the refrigerant knowing that temperature and pressure are given? And it just happens that, yeah, I don't even have to interpolate. Somebody was kind to us. And so they pick off the value of H, 248.89 kilojoules per kilogram. How about the value of H2? At that pressure and temperature, 287.44 kilojoules per kilogram. So let's just continue to input our numbers. We have negative 0.4 kilowatts for Q dot. We have a mass flow rate of 1.7 kilograms per second. We have an enthalpy in, 248.89. Enthalpy out, 287.44 kilojoules per kilogram. The kilograms go. Kilojoule per second is precisely a kilowatt. And we calculate that the answer, W dot CV, is negative 65.9 kilowatts. Let me ask a couple questions. The exit enthalpy, is it greater or lower than the inlet enthalpy? Yeah, look at the magnitudes, it's greater. Exit enthalpy is a measure of internal as well as flow work. It's U plus PV. It's a measure of the energy of that flowing fluid. Right? Internal energy plus PV, which represents flow work. That's enthalpy. So why was this so much higher? Both because of temperature as well as PV, the pressure term. Okay. Well, with that, I'm going to stop. Do you have any questions for me? If you didn't look at your exams, I'll be in my office. If you have any questions, please ask.
I was going to ask that too.